Hey, we're marking the take-home quiz. Here's the first few answers. 4, 2, 3, 4, 4, 1, 6, 2. Sorry, I forgot to hit play. Complete the following calculations to the correct number of sig figs. Okay. Multiplying and dividing is the easier one. I'm going to actually multiply and divide, and then I'll adjust the sig figs afterwards. So 3.654 times 19.2 equals, now that's my answer. Oh, how many sig figs does my first term have? 4. How many does my second term have? 3. How many sig figs is my final answer? 3. So it's going to be 70.1 or 0.2? 0.2. 70.2. Number 2, same idea. I'm going to go 106.3 divided by 12. This has 4 sig figs. This has 3 sig figs. I'm going to go, sorry, 2 sig figs. I'm going to go to 2 sig figs, 8.9. Yes? If I'm wrong, let me know. Number 3, 2.3654 divided by 7. How many sig figs am I going to go to here?
1.
Which means the best I can write is 3,000, or 3 times 10 to the third if you went to scientific notation. I'm doing a lesson today on scientific notation, so you don't have to, but 3,000. Now, multiplying and dividing is a different rule from adding and subtracting. Adding and subtracting, a little trickier. Kiara, how many decimal places does this first term go to? How many decimal places does the second term go to? How many decimal places does the third term go to? 3. You know what the smallest number you just said was? I'm going to go to 1 decimal place. And did you hear? I never said sig figs. For adding and subtracting, it's not about sig figs. It's about which decimal places you know. And the first decimal place that I don't know is after decimal place number 1. So I'm going to, this is if you don't want to write them vertically. This is how you can kind of keep track of it in your head. I'm going to go 12.45 plus 19.2 minus 2.656. But Kiara, you said I have to round to that decimal place right there? Yeah. Oh, it's going to become a 0 because of that. Oh, that's going to bump that up. I think it's going to be 29.0. Number 5. Oh, multiplying and dividing. I think that's the easier one. It's going to be the 3 sig figs, I think. 4.379 divided by 123 times 525. What did I say, to 3 sig figs? So it's going to be a 1, and I'm going to round off right to there. The 6, because of the 9, is going to become a 7. It's going to become 18,700.
Sure.
18,700. Or 1.87 times 10 to the 4th if you went in scientific notation. Number 6. How many decimal places does this last term have? 4. How many decimal places does the middle term have? 2. How many decimal places does the first term have? 0. I'm going to round off to no decimal places. And again, it's nothing to do with how many sig figs there are. It's what decimal places you know when you're adding and subtracting. So it's going to be 241 plus 26.67 minus 5.6632. I'm going to round off right to here. Oh, that's a 0, so the 2 will stay a 2. Final answer, 262. C. Round the following off to the correct number of sig figs indicated in the brackets. Okay. Round this off to 3 sig figs. 1, 2, 3 sig figs. And it would be a 7, yes? Because there's an 8 next to it. Round this off to 2 sig figs. 1, 2 sig figs. Mr. Duick, wouldn't the 6 round up? Because wouldn't this become a 0 and that become a 0? No, hey, I'm rounding off right to there. That's the only one I look at. Is it a 4 or is it a 5? It's a 4. The number stays the same. If it was a 5, I would round up. You don't start way over and keep dominoing your way up all the way until you get to the amount of sig figs you want. 1,600. Give yourself a score, please, out of 16. Can you make sure your name is on it? So we're looking at the graphing the thickness of a textbook versus pages. I got a slope of about 0.3043-ish, give or take. And my y-intercept was 1.4. Your equation might be different. But then what I asked you to do was find the thickness for 225 pages using the equation and 1,000 pages using the equation. And I said the way you were going to do that was you were going to plug the 225 into here and plug the 1,000 into here. When I plugged the 225 into my equation, I got 9.1. Well, what I want to do now, and this is part of what you're going to hand in, I want to teach you how you can do what's called an error analysis. We want to find out how accurate we are. Now, your numbers may be different from my numbers, but if you take your equation, whatever your equation was, and you stick a 225 right there, I called mine T for thickness at 225 pages. I got 9.1 millimeters. I don't know what you guys got, but can you find that number, whatever number you got when you plugged a 225 into your equation of your line, and write that down somewhere?
Times 225?
I think it was 225 pages that I asked you to find the thickness of, right? Use your equation, I said, to calculate the thickness of 225 pages and 1,000 pages. You'll also later on be doing for 1,000 pages, but that you're going to try on your own. So all of you have a thickness for 225 pages, a theoretical thickness based on your equation. Okay? I handed out 3 textbooks. Those of you that have the textbooks, we're going to do an error analysis. And you can write this down. Heck, I'll even underline it. Woohoo! We'd like to find out your percentage error, and the way to calculate the percentage error is as follows.
Did you say to write this down?
Yeah, write this down because you're going to be doing this. You're going to add this to your textbook lab handout. So you can write this on the same piece of paper, on the back page of the paper, or you're going to hand this in stapled to the textbook lab. Okay? Those of you that have the 3 textbooks, can all of you turn to page 225, and can you carefully with a ruler measure the actual thickness? So there's 3 of you, right, that I handed out? I want 3 values. We'll take an average because I'm worried one of you might not know how to use a ruler. Not mentioning any names. So turn to page 225. Measure the thickness, please, and tell me what you get. Thickness? Whoop. Can't type. Matt, what'd you get?
I got just under 9 millimeters.
Just under 9 millimeters? Jeanette, what'd you get? 8 millimeters? 9 millimeters? So I heard 9, just under 9, and 8. You know what? I'm going to say, how about 8.5 millimeters is what we'll go for the actual thickness. What's my theoretical thickness? What did I get when I used my equation? 9.1. I'd like to see how accurate I am. I'd like to do a percentage error analysis. So you'll use your numbers, but for the actual thickness, you can use the 8.5 millimeters. The percentage error is calculated as follows. Jacob, see this number right here, the actual thickness? Read it out to me nice and loud.
8.5.
See my theoretical value? Read it out to me nice and loud.
9.1.
Go bigger minus smaller. You want to find out how far apart they are. So I'm going to go 9.1. You're going to go whatever your theoretical value is. Oh, but if your theoretical value is smaller, go bigger minus smaller. Minus 8.5. And you always divide by the actual correct value. What's the actual correct value? The one that we measured, which was what? 8.5 millimeters. And then I'm going to go times 100% to change it into a percent. Okay? So for me, I'm going to go like this. Your numbers might look different. But for me, I'm going to go 9 times 100%. 0.1 minus 8.5 divided by 8.5. Does anybody see what I've done wrong already, by the way? This is wrong. Yeah.
Divided by, because rules of mass division.
I got to put the top in brackets. You know why? Because there's two numbers up there. My calculators, by default, assume that stuff is supposed to be on top. Yeah, so I got to type it like this. Bracket, 9.1 minus 8.5, close bracket, divided by 8.5 times 100. I'm within 7% of the actual value, which is pretty good. I'll take that.
What is the limit?
I'm not going to mark you wrong, but with the equipment that we're going to be using for most of our stuff, we'll be happy if we're within 20%. Because most of the time, it's human reaction time. Big, big challenge. This one was straight measuring. There was no, but anytime we're timing things, trust me, you guys suck. You do. Okay. Anybody get less than 7% with theirs? I'm impressed. So I'm going to put 7. In fact, I'm probably 7 point. Oh heck, 7%. Those are three. Yeah.
What if like we got 8.5 before?
And it.
0 now.
So you are 0% error. You're bang on. Well done. Means you're probably very careful. Those three of you that have the textbooks right now, can you also put the actual thickness for 1,000? Because you'll need that to do your error analysis. So actual thickness for 1,000, for page 1,000. Can you turn there and measure that? And we'll do the average again. Okay, then, can you actually measure page 1,000, please?
Sure.
Matt, what'd you get?
3.5 centimeters.
Sorry? In millimeters, please.
35.
35. Anybody else? Janaya?
35.
35? Kayvon?
Yeah.
Yeah.
This is now numbered.
What's the weak link in that chain? Uh-huh.
Wait 1 second.
I'm waiting 1 second.
Okay. 1, 2, 3. 35.
35? Okay. So the actual value is 35. Put 1,000 into your equation. This is how we can find out how accurate our line of best fit is. There's other ways. You can do a least squares regression analysis. There's all sorts of mathematical tools. But the simple one is, hey, if you know what the answer was supposed to be, why not find out how close your theoretical answer is? Percentage error. Okay? You can do it right now really, really quickly. And when you're done that, if you'd be so kind as to get out the Pendulum Lab, please. The one that looked like this. And again, I'm using another student's data. I'll see if I can get the whole graph on there. Pretty close. So on the Pendulum Lab, ideally, your graph should look kind of like this. In fact, I actually looked up the theoretical equation, the equation if we were doing it in a vacuum, the equation if our ropes had no friction and weren't rubbing against the meter stick, the equation if people weren't walking around the room and sending vibrations through the tables and transmitting that down the end of the stick and causing that to, the theoretical equation. I graphed it and I got that shape there on my graphing calculator, and you can see we're close, at least this person's data. I'm not going to be hugely fussy if some of your data is off, but I noticed a few of you did get pretty close to this graph. I know you guys did. Very, very nice. What I want to talk about are the questions that are being asked. So the first question it asks, and I got to make this big again now. It says, according to your graph of period versus length, how long must your pendulum be if it is to be used as a 1-second clock? So if I go to my graph paper, for me, on my data, 1 second is right there, and if I drop down, how long is my pendulum for 1 second? Pretty close to 20 centimeters. About, yay. Okay. This is why grandfather clocks primarily come in two sizes. There's the wall-hanging ones. They have a pendulum about this long, and they go click, 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 back and forth once every second, back every half second, every half second, every half second. Or if you want a pendulum that's 2 seconds long, for this graph, for me, it ended up being yoink, yoink, almost 100 centimeters, just bang on close to a meter long. These, Doug, are the stand upright grandfather clocks, the ones that are about head high. If you look at that pendulum, it's about a meter long, and they go click, click, click. They swing halfway once every second, there and back, 2 seconds. It's very difficult to build a grandfather clock of any other size because it's awkward if your period is 1.32 seconds and you're trying to somehow synchronize. It's a pain. You're going to say, you know what, I'll shorten the pendulum to a 1 second pendulum period length. The gearing system is way easier now. Oh, except when you did your pendulum, what happened gradually to the size of your swing? Got smaller and smaller and eventually came to a? How do they get around that with a grandfather clock?
Mechanism.
Begins with the letter W. And this is where you guys are the digital Cole! What?
Winding?
Wind it. Oh, there's a spring in there. And when you're winding it, that spring is attached to a gearing mechanism, which adds just a tiny bit of energy on every swing or every few swings. And it's enough to keep it pretty good. Within a few seconds every week, which for the longest time was revolutionary and sufficient. Until we had digital clocks, grandfather clocks, pendulum-based clocks were amazing because you and I could be 50 miles apart and we could know what time it was for each other within a couple of minutes, which up until then, you know, sundials and things. Who knew then, right? So they were a nice invention. But that's why, keep your eyes open. You don't see grandfather clocks in too many different sizes. Two main sizes. There's other ways of setting. There's the Navy clocks. Those go with a spinning weight mechanism. Those are the ones that sometimes sit on a mantelpiece. There's all sorts of other different types of ones. And digital, of course, is really the way to go. Those are much more accurate. Those use a resonance frequency of quartz, I believe, or something to that effect. So that lets you answer question 1A, but answer it from your data. You should be pretty close to my data, though. Galileo showed that actually for a pendulum, it doesn't matter what size the mass is, as long as you're not doing huge, huge swings. As long as it's a fairly small swing, the masses cancel. If we had done the same experiment with a 1 kilogram instead of a 100 gram mass, we would have got the same answers. Except we would have needed thicker string. To increase the period from your pendulum from 1 second to 2, by how many times must I increase its length? How long was my 1 second pendulum? 20 centimeters. How long was my 2 second pendulum? 100. How many times bigger is that? 5 times bigger. This is why I said this is not a linear graph. When you're twice as big with the time, you're not twice as big with the length. You're 5 times as big with the length. It's not a nice linear graph. It's a curve. Did I say you had to answer the follow-up?
No.
No? Okay. So you can finish later on in class and hand that in later on in class if you want to as well. But we are now going to move on. You need your calculators out, please. Lesson 4, dimensional analysis, a hugely useful skill, but we're probably not going to get to that until Tuesday. And scientific notation. Scientific notation, a great shortcut. How to write really, really big and really, really small numbers without having to write really, really big and really, really small numbers. In physics, we're often stuck with really, really big and really, really small numbers. The mass of an electron, for example, is 0.0000000, 26 zeros, and then a 911. Who wants to write that out? Scientific notation. How does scientific notation work? It says write the following in scientific notation. 310,000, I would write the 3 and put a decimal. Then I write any significant digits after that. A 1. Are the zeros significant? No. I replace all these zeros and part of the 1 with a power of 10. What I say is this. The decimal was originally there. I've moved it between the 3 and the 1. I've moved it 1, 2, 3, 4, 5 places. And I show that by saying I'd multiply that by 10 to the 5th. Who has never seen scientific notation before? You guys do it in Science 9, is that right? Or Math 9? Science 9. Both? Okay. Well, we're doing it here too. Example 2, 12 billion, 44 million. I write down the first digit, 1. I put a decimal point. I write down any significant digits after that, a 2, a 0, a 4, a 4. The decimal point was originally here. I moved it here. How many places? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Times 10 to the 10th. Three and 4 are kind of dumb examples in that I would never write 31.62 in scientific notation. The reason, Brad, is to me, scientific notation is supposed to be a time saver and a shortcut. 31.62 is going to be 3.162 times 10 to the... That's more writing than just writing it out. So my rule is, unless they specifically say, give me an answer in scientific notation, if it's shorter to write it out, which basically means if it's in the hundreds or the thousands or the 10,000s, yeah, write it out. If it's bigger than that, yeah, go to scientific notation. Same for small decimals. Like I would never write number 4, 10.0 in scientific notation. I would write 10.0. It's less work. But we should know, in case we get this number in scientific notation, what it looks like. So example 3, I would go 3.162 times 10 to the what? Times 10 to the 3? You're saying I moved the decimal point from here to there? I don't think the decimal point was originally 3 over. Where is the decimal point right now, Joel, in the original number between what two numbers? Ah! 10 to the what? You're right? 1. You guys have had me for a couple of weeks. Am I going to write the 1 if it's unnecessary and implied? I'm lazy. You can put a 1 there. Go ahead, Aaron, knock yourself out. Got your name right finally. It's not wrong. Can't make me. Your calculator might demand that you put a 1 there if you were typing this in your calculator in scientific notation. Abraham, I wouldn't type it into my calculator. It's way faster to type 31.62. It's 5 keystrokes as opposed to this many. Number 4, which is the number 10. 1 point. How many sig figs is this number? That number there. How many sig figs? You just had a quiz on it. It's 3. 3. Whatever they measured, they got an answer of 10.0 and something else, but that wasn't accurate. They got 10.0. This is 3 sig figs, which means I told you, you write every significant figure down. This time you would have to write 1.00 times 10 to the what, Joel? Yeah, am I going to write the 1? No. And again, let me clarify, Amanda, I would never write this in scientific notation unless they made me. 1, 2, 3, 4 characters to type that in. 1, 2, 3, 4. Forget it. That's dumb. Decimals. How do I do small numbers? Very similarly, but we're actually dividing by 10. And how do we show that we're dividing by 10? We do something with the exponent. What? Negative. This is going to be 4.5, because the zeros in front are not significant, times 10 to the negative what, Enzo?
-3.
Yes. But I'll be honest, I would not write that number in scientific notation either. It's easier to write 0.0045. Definitely number 6 I would write in scientific notation. Pretty sure. Roy, what am I going to write? First digit, what am I going to write? For example 6, the one that we're currently on. 7.06 times 10 to the negative what? Is it 9? 1, 2, 3, 4, 5, 6, 7, 8, 9? Or are you just a German saying no? Yeah, okay. 9. It's a joke. Doppler effect. Yeah. I'll get it. Hey, number 7. How many sig figs is that? Careful. Mm-hmm. 6.00 times 10 to the negative 1, 2, 3, 4, 5, 6, 7. Where scientific notation does shine, Cliff, is when you glance at it, you know instantly how many sig figs there are in your original number. Hey, that's 3 sig figs, that's 2 sig figs, that's 4 sig figs, that's 1 sig fig. If the scientific notation has been done right, all you do is you count the number of digits in front of the 10. So it's convenient that way. Number 8, I would never write this in scientific notation either, but for practice. Doug, how many sig figs does number 8 have?
It has 3.
So I'm going to write 6.30 times 10 to the... How many places have I moved the decimal point this time? Doug's shaking his head. So what am I going to put up there as a number?
0.
I got to put a 0 there, because anything to the 0 power is actually just a 1 when you simplify it. And again, let me clarify, would I ever write that, Colt? No. Why would I write 6.30 times 10 to the 0 when I could just write 6.30 and quit? You also need to be able to easily go from scientific notation to what's called standard form, or fixed decimal notation on your calculators. The reason they call it fixed decimal notation on your calculators is they want to use the letter S for scientific, the letter F for fixed. So when you're mucking around with your calculators, if you see an FSE, that often means you can flip between fixed decimals, scientific notation, and engineering notation. Write the following in standard form. I write the first digit. Stefan, what's the exponent on the 10? I'm going to go like this. 1, 2, and then fill the rest in with zeros. 3, 4, 5, 6, 7. It's 23,400,000. Two. 1.5 times 10 to the 3. Write down the first digit. Abraham, what's my exponent on the 10? So I'm going to go like this. 1, and then 2, 3. Count any significant digits, and then keep adding zeros until you get to the exponent. 1,500. Three. What is anything to the 0 power? Cole, you're saying this is really 3 times 1? Which is just what? 3.0? Ah, no, that'd be 2 sig figs, and this number clearly only had 1 sig fig. Number 4. Okay, negative decimals. Very similar. 0 point. Jordan, what's my exponent?
-5.
So I'm going to go like this. 1, 2, 3, 4. What did you say the exponent was? This is where I'm going to start writing on the 5. 1, 6, 7. Right? Example 5. 1.3 times 10 to negative 8. That's going to be 0 point. Negative 8 means I'm going to go 7 zeros and then start writing numbers. 1, 2, 3, 4, 5, 6, 7, 8. Number 6. 3 times 10 to the 8th. 3. 1, 2, 3, 4, 5, 6, 7, 8. For those of you who are wondering, 3 times 10 to the 8th, that's the speed of light in meters per second.
Are we allowed to use commas instead of spaces?
Yeah, I use commas when I'm handwriting. I know it's preferred under typing to use spaces for some reason. I find commas, pairing them up in 3s, makes it way easier for me to read the numbers. There's sort of different rules for typing because it's neater. Later on, we look at vectors as well. When you're writing a vector and you're typing it, you do it in bold font. It's very, 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 very tough to handwrite bold font. So we use a symbol for a vector when we're handwriting. Get your calculators out. You need to know how to type this in. It says calculate the following. How many terms are on top in example number 1? 2. Are they being added or subtracted, or are they being multiplied? Okay, for what it's worth then, you can be sloppy with brackets here because your calculator by default assumes if you hit times, it's on the top. You could be paranoid, Abraham, and put the whole top in brackets. Nothing wrong with that. But for what it's worth, I can be a little sloppier with multiplication. Now, if there was 2 terms on the bottom, I would have to put the bottom in brackets because your calculator doesn't assume terms are on the bottom. Where does it by default assume terms are? On the top. So how am I going to do this? You need to find your scientific notation button. It's an EXP button or an EE button. You need to go 1.34, hit your scientific notation button, and get a 7. And if you can't find it right now, now is the time to call me and I will come around and help you. Crunch the numbers. I'll see what I get here. And then we need to get your answer to display in scientific notation, which is also going to be an adventure for some of you, depending on your calculator. And I will come around and assist you shortly. But the answer that you're looking for is 1.634 times 10 to the negative 9. If you can't get that to appear, now is your chance to call me, and I will help you. Forgot to start the lesson. So, example 2, 1.2. Oh, and number 1, 1.6 times 10 to the negative 9. 1.7 times 10, 1.64 times 10 to the negative 9. I guess 2 sig figs is what I would do the first one. We need to practice with our calculators a little bit. So we'll start part 2 on Tuesday. This is using metric prefixes and dimensional analysis. But what I do have for you right now is a little bit of homework. So on this sheet, I got to repeat myself. Sorry, folks. Try doing section A 1 through 9 odd, section B 1 through 9 odd. I would like you to try all of number C, because C seems to be when you're using your calculators where kids start to have troubles with dividing and weird stuff. Leave your answer in scientific notation. If you're not sure if you did it right, check with a neighbor. I will try and make up an answer key, but I might not get to it this weekend. Okay?